What we want to do now is talk about the difference between defining a variable and declaring a variable. And this is particularly important in object-oriented programming, although it really should be important to any programming language, and it should be important to any programmer. Define and declare are not the same thing. We tend to use those two words interchangeably. I can point you to a whole host of literature that uses the two terms as though they were the same thing, and they are not. And this makes communication between two different programmers very difficult because at many times they tend to be talking at odds to one another and don't even realize it. Declare creates an attribute list in a symbol table, and that's all it does. In other words, the purpose of a data declaration is to tell the compiler the name of the variable and its type. It does not allocate memory for it. The most common example is the method signature that we see in so many places in code. And if you look at that, it says public int days in month and then parentheses int month. The signature for any type of a method is really everything that goes from the word public in that line all the way to the closing parenthesis. And a signature for a method or a data item must be different for it to appear in a program. You could not have the same signature in the same program, or you would get a duplicate definition error. Now, in that line, in that signature, look at the words between the two parentheses, and it says int month. All the purpose of that piece of information is to tell you the data type that's going to be associated with that particular data item. It does not cause any kind of memory to be allocated for it. By the time this method is called, that variable named month already exists on a stack, and the only reason that we even have that in the symbol table is so the compiler knows how many bytes to grab off the stack and call it month. Memory has already been allocated. So it's simply to create an attribute list to let us know information about what month is. It serves no other purpose. So int month is there. It tells us what's been passed. The mechanism in most modern languages will be that that particular piece of information is passed on the stack. Now let's talk about defining a variable versus a data declaration. If you define a variable, it also causes an entry in the symbol table that will tell what the variable is, maybe an int. It will give the name of the variable, but the main difference is it causes memory to be allocated for the data. For example, suppose that we have the definition int I. In this case, we're just simply defining an integer variable with the name I. And in the little graph on the other side, or the pictorial, you'll see the variable I at the top of the graph. And then you'll see two legs coming down for L value and R value. These two terms go back to assembly language days when L value stood for location value and really pinpointed in memory where that particular data item was going to live. And then the R value was the register value. In other words, it was what piece of information was actually stored there. In other words, the data value itself. What we're saying now is when that line is parsed by the compiler int I, semicolon, the compiler reads the semicolon and it knows it has a full language statement. It will check it for syntax, and assuming that it's okay, in other words, it's a correct statement for whatever language it is that we're talking about, the compiler sends a message to the memory manager. In this case, since we're assuming that we're running under Windows, it sends a message to the Windows memory manager and says, I need 4 bytes of data to store a variable of integer data type. Windows will then pass back, well, it will inspect the free memory that it's allocated and has control over, and it will send back a memory address of where I can live. And in this graph, we're saying that the variable I lives at memory address 900,000. So the location value of that particular variable I resides or lives at memory location 900,000. The L value is what is actually stored there. So now if we put in a second line of code and actually do an assignment into the variable I equals 10, what you really are doing then is you are changing the R value from some unspecified unknown value to 10, and that value is going to be located at 900,000, which is the L value for that particular variable. I've developed a little simpler way of explaining all of this with something that I call the bucket analogy. Let's consider another assignment statement, int val. We now know that that's going to result in a symbol table entry that's going to name the variable val, and it's going to assign it enough storage to hold an integer variable. In most cases, that's going to be 4 bytes. This is going to give a specific memory location to the variable named val. In other words, the call to the Windows Memory Manager or whatever operating system it happens to be running on is going to pass back a memory address that gets filled in for the L value of that particular variable. If the Windows Memory Manager passes back a memory address at 750,000, what we're doing is we're creating a bucket at memory address 750,000. So the L value then becomes the home for that bucket. However, the size of the bucket is determined upon the type specifier for the variable. So we now know 2 things about the bucket. We know where it is, and we know how big it is. It's big enough to hold 4 bytes of data. If we take the statement and do an assignment like we did before, and we say we're going to move the value of 10 into that bucket, then that same graph now will have, or that same picture will have the memory location, but if we look inside the bucket, we now see the value of 10 represented by the 4 bytes of data. Now consider this statement. Double temp equals 44.5. This is going to create an 8-byte bucket because doubles tend to be 8 bytes in most languages. And it's going to move into that memory location of where that bucket's located, the value of 44.5. Now, suppose that we try this. We attempt to take the value val, which is an integer, and we attempt to move the contents of temp into val. The last line creates an error message, and the reason that it does this is because you're trying to pour 8 bytes of data into a 4-byte bucket. Anytime that you try to do that, you're going to have data lost. You're going to have 4 bytes of water or whatever you want to think of. 4 bytes of data are going to spill out someplace. And the compiler cannot allow that, so it will flag that as an error, and it'll draw an error message. This is what we mean by most OOP languages are strongly typed. In other words, it's not going to let you mismatch the type of the data where you're involved in assignments or something like an assignment. So the lost data will always cause a strongly typed language to generate an error message. To fix this, you use the word int inside of parentheses, which is a cast. And really what a cast is it's a funnel that says, okay, look at the data that's coming in, the 8 bytes, and sort of filter out the 4 bytes that we can that don't make sense, throw those away, and use the funnel to funnel what's left into the 4-byte bucket that's stored wherever val happens to be stored in memory. Now, let's look at these statements. Same thing, only the difference is now we're taking the value of val and assigning it into temp. The bad thing is compilers don't generate an error on this. I think they should. And the reason is because you have a type mismatch. You're taking an integer and assigning it into a double. But because you're taking 4 bytes and the contents of a 4-byte bucket and pouring it into an 8-byte bucket, that's fine. There's no data lost. As long as there's no spillage involved, if you will, the compiler doesn't flag this as an error. I think this is what I call RDC, really dumb code. And the reason I call it that is because your intention isn't indicated by the code itself. In other words, someone could look at that and say, well, this guy's doing a type error. So the statement doesn't generate an error, but I think it should. There's no data spillage, so it's not going to generate a compiler error. I would rather see that last line rewritten so that we say int equals open parenthesis, double, close parenthesis, space, val, semicolon. That way you've documented that you know what you're doing. You are attempting to take an integer and pour it into a double. It doesn't do anything from the compiler's point of view, but it does do something from the person who's responsible for reading the code. It tells that person you knew what you were doing and you did it intentionally. The line as it stands now, just saying temp equals val, is what I call a silent cast, and I hate those, and you should too. So how does the bucket analogy work with a reference type? So far we've been talking about value types like ints, chars, bytes, so forth. What happens when you have a string variable and you say something like string my name equals Lynn? You saw earlier that reference variables have an R value that is the L value of where the data resides in memory. In other words, if you're familiar with other languages, reference variables are actually pointers. So therefore, looking at my name bucket, if you find out where that bucket is located in memory and look inside of it, the conclusion is that Lynn is going to be stored at a memory address that is stored inside of that bucket named my name. So anytime we have a reference variable, the value type have a bucket and the data is stored in it. A reference type has a bucket with a memory address stored in it. It also means that all reference buckets are the same size. They're going to be the size of a memory address. And in most modern languages, memory addresses are 4 bytes. So the size of the bucket with a reference variable is always going to be the same size, 4 bytes. And the content of a reference variable can have only 2 states. It can be null, which means it doesn't point to anything yet, or it can have the memory address of where the particular data is stored. In the statement, the program statement at the top of this slide, it says string my name equals Lynn. That will have a valid memory address of where the word Lynn is stored in memory.